Good day everyone. Today we're gonna present about our mini project of modern control system subject. First of all, let me introduce you my team. My name is CHANG and my team member is Fang, Xiang and MOHGAN. Next, what is about this mini project? Let me introduce you. This mini project is about a lead-lag compensator. What is lead-lag compensator? A lead-lag compensator is a component in a control system that improves an undesirable frequency response in a feedback and control system. It is a fundamental building block in classical control theory. Next, what is the objective? The objective of this mini project is introduced to lead and lag compensator and understanding the phase and magnitude response. Second, is able to identify stable response and unstable response. Third, is able to identify and calculate phase margin, gain crossover frequency, and phase crossover frequency from the block plot. Next, let's move on to the question of the mini project. For question number 1, we need to find or create a transfer function with at least one k-value, 2 zeros, and 3 poles and substitute inside the equation below. For this question, we assume the k-value equal to 0.1, 2 zeros A equal to 200, B equal to 300, and 3 poles C equal to 1, D equal to 20, E equal to 30. After that, we substitute inside the equation and we can get the equation of the transfer function as below. So, we move on to the question number 2. Based on the above transfer function, we use the Scilab and dot plot technique to illustrate its amplitude response and phase response. This is the coding that we use for this question in the Scilab. And this figure shows the coding used in Scilab to illustrate the transfer function, which is this transfer function. So this is the dot plot that we get after using the coding that we showed just now. After using the coding in the Scilab, the dot plot of amplitude response and phase response of the transfer function is shown. We obtain the gain margin is 19.794 and gain crossover frequency which is 1.3926 Hz. The phase margin is 60.8049 and the phase crossover frequency is 5.369 Hz. So what's so special about the phase margin and the gain margin? Phase margin is a measure of the distance from the measured phase to a phase shift of negative 180 degree. In other words, how many degree the phase must be decreased in order to reach negative 180 degree. Gain margin, on the other hand, is measured at the frequency where the phase shift equals negative 180 degree. Gain margin indicates the distance in dB from the measured gain to a gain of 0 dB. This value 0 dB and negative 180 degree are important because system instability occurs if this value meets. Gain and phase margin represent the distance from the point at which instability could occur. The greater the distance of margin or the margin, the better, because higher gain and phase margin mean greater stability. A loop with a gain margin of 0 or even less would only be conditionally stable and could easily become unstable if gain change. So that's all for my part. Thank you.
Good day to my lecturer. My name is Fang Xiang and my number metric is 221022293. For question number 3, we need to use the lead compensator to further improve 10% of the current phase margin for the response. So for the first step, we need to find the current phase margin from the Scilab, which is 60.8049, which we found from question number 2. Then we need to improve the value by 10% and we will get 66.8854 degree, which is our required phase margin. After that, we can use the Vmax formula to calculate the maximum allowable phase shift or maximum phase lead Vmax. We use the phase margin required minus current phase margin and add an additional 15 degree for safety margin. So in the end, we will calculate 21.085 as our Vmax. Then we can use the Vmax formula to find the alpha, and we get alpha equals to 2.1235. After that, we use the gain crossover frequency formula, and we can find the tau value by subbing the gain crossover frequency. But first we need to change the gain crossover frequency into unit radian per second in order to find the tau value. So for 8.75 radian is equal to the gain crossover frequency, then we can move and get tau equals to 0.0784. After that, we can substitute our tau and alpha into our general equation for our lead compensator, and we will get this type of equation for our lead compensator. Okay, this is the plot result and the coding I used to find the new phase margin and gain crossover frequency. Okay, as we can see, the plot is like this. It's still stable of right below and left above, and the new phase margin is increased by when you use the 180 minus 115.651, you'll get around 64.35, which is you get from the difference and from here phase margin. So from this we can know the phase margin is increased by around 4, and it reached around our required phase margin, which is 66.8854.
A very good day everyone, my name is Darwin, and in this video I will be presenting about lag compensator based on our mini project. Firstly, we should be aware of the phase margin based on the initial transfer function from the equation. Since we need 10% improvement, we should add 10% to current phase margin and add another 5 degree as safety margin. From here, we will be able to find the new gain crossover frequency. Since Scilab is showing it in frequency, we have to convert them into radian per second. From here, we are able to find the gain and the new gain crossover frequency. Using this value, we can now find the value of alpha from 20 log alpha is equals to the gain and the new gain crossover frequency. Set 0 a decade below from the new gain crossover frequency. Using this value, we can now find the value of tau. Then we will insert the value of alpha and tau into the phase lag transfer function equation. Using Scilab, we are able to see the 10% improvement in the phase margin. Since it's lag, we are able to notice that the new gain crossover frequency is smaller or falls before the original gain crossover frequency.
So for question number 5, we will ask that which compensator can be used to achieve 10% improvement for the phase margin. So throughout completing this mini project, we found out that we can increase the system phase margin using both lead and lag compensator. The lead compensator provides a lower new phase margin value with 64.35 compared to the lag compensator, which provides a higher new phase margin. So obviously it is a better option for our transfer function to choose the lag compensator because it produces a higher new phase margin after compensated. So what did the lead compensator do? It moved the system work plot higher at a required frequency to increase transient responsiveness and stability. On the other hand, a lag compensator lower the gain crossover frequency to cause phase lag and reduce gain at higher frequencies. Lag compensator is often used to decrease steady state error and increase steady state accuracy. So in conclusion, it is proof that a lag compensator is a better option to enhance the phase margin because it provides a higher final phase margin compared to the lead compensator. That's all for us. Thank you.